Hi.
Bom dia.
Bom dia. I thought I was in the wrong room because there was nobody.
Well, apparently we are being panelists, so hopefully we're in the right room.
Okay. Let me try to share this. Well, do you see something?
Yes, your slides are visible. Very well.
Okay. I was, because I don't see, so I don't know. Just trying to understand. Okay. Yes, I can stop this. How do I do this? Speaker video. This is the menu. Okay, but how do I stop sharing the screen? I don't know. Maybe here. Stop video.
Okay, so I don't see anybody else from the conference committee here. Let's wait for a bit.
Yes.
Good morning, everyone.
Good morning.
Okay, shall we start? Okay, so we start the session today, so our last day, and it's my pleasure to introduce you Leila Ribeiro. Leila is a full professor at the Informatics Institute at the Universidade Federal do Rio Grande do Sul. She holds a bachelor's degree and a master's degree from the same university, and a PhD degree from the Technical University of Berlin in 1996, with a dissertation on semantic models of computing. She also has a postdoc from the University of York in 2008. Her research focuses on the fundamentals of computing, and she works mainly in the specification and formal verification of software engineering applications, bioinformatics, computational models, and computer science teaching. So welcome, Leila. Thank you for being here. You can start, please.
Okay, thank you very much for the introduction. Let me share my screen. So, can you see now the slides?
Yes.
Okay. Okay. So, I'm very happy to be here at SBMF again. Unfortunately, we are not present, but maybe next years. I was invited to talk about modeling languages and specifically to tell you a bit about my work that I have been doing for many years now on graph grammars. That is one modeling language. So my idea is to say something about what modeling languages are, and then introduce graph grammars and something about verification of graph grammars. So let's start about introducing what modeling languages are. So first, models are actually abstractions of the reality. So a model may be, we can build a model by abstracting away from different aspects of a system. So and to describe the model, we need languages. And what we call a modeling language in computer science is actually an artificial language. That means usually natural languages are not modeling languages, although we can use a natural language to describe things, but we don't call them modeling languages. And so we use different kinds of languages that may be textual languages or graphical languages. Very commonly, we use graphical languages as modeling languages, like in UML, for example. We have lots of different modeling languages that have some graphical layouts. And with these languages, they may describe structure of the system, structural aspects, but also behavior of systems. So here are some examples of some of the UML language. UML is a set of modeling languages. We may use UML. Some UML languages are very suitable to describe the system, like the structural part, like components or the classes that build the system, or objects or packages at different levels of abstraction. So we may use modeling languages at many different levels of abstraction. We could also say that programming languages are modeling languages at a very low level of abstraction. But typically when we speak about modeling languages, what we have in mind is that they are at more abstract levels, that we are using them for specification of systems at this level, although programming languages could also be modeling languages. So why do we use graphs? So graph is a kind of way of organizing information that is in a way very intuitive. We use graphs for many things to try to represent and describe many different kinds of information in our lives. So we see the graphs in maps and subways or descriptions, even DNA or structure of cells. We we are very, very much used to using this kind of structured graphs or trees that are special kinds of graphs to describe not only the statical part of the system, but it could also use graphs to describe behavior, like flowchart diagrams or Petri nets, or there are many graph representations of behavior. But typical, or of a state, like if you have a map is a graph representation of a state of a system, of the cities and roads, or social networks, internet. So there are really many examples of the reality that we can represent as graphs. So just statics or dynamics of the reality can be represented as graphs. And actually it makes it easier for us to understand what we are seeing. Usually graphs are, okay, if they are not very huge, they are, for us humans, we can understand better something if we see a graph. If the graphs become very large, then it starts being difficult for us to understand what we are seeing. But this is also true if you represent the states of systems in any kind of description language. If the state is very huge, it's difficult for us. So when we speak about graph grammars is actually a very old way of specifying systems that came from Chomsky grammars. You know, Chomsky grammars, we used to rewrite strings. So we have one string and then we replace that string by another string and keep rewriting. And so this is the basis of our model of our formal language theory. And with graphs, we do more or less the same, just that instead of rewriting strings, we rewrite graphs. And using graphs to model system specification, to describe the system specification, usually is like we describe the states of the systems as graphs, and the transitions or the transformations or state changes are described by graph transformations. So we have a set of graph transformations that describe the behavior of a system. So with graph grammars, we can represent the behavior of the system at a very intuitive level, because we can see the graphical structure of the state as a graph. And then we just see, oh, the graph is like this, and then at the next step, it will be like that. So it's very intuitive. So even people that are not from computer science can understand the specifications. And this is very important when we need to validate our specifications with a client or with people that do not really are from our field. So therefore, graph transformations are nice in this sense. This formalism is data-driven. I will speak about this a little later. So we have very simple concepts that we have a state represented by a graph, state changes, but we can build a very solid theory behind. And what is nice is for some person to use this theory or use graph transformation, you do not have to be an expert in theory to understand what's going on. Theory is very nice if we want to build tools to analyze the systems, but the people that are using those tools, they do not really have to understand what is going on at the background. Just understanding the basic the basic behavior of graph transformation is enough to understand what's going on. So in this talk, I will talk a bit more about the algebraic approach to graph grammars. There are many different approaches to graph grammars, and the difference basically are which kind of graphs you use, and how you describe rules and how you apply rules, because these are the basic things that you do in a graph grammar. And there are many different ways to do this. And in the algebraic approach, we do this all the theories based on category theory. In this talk, I will not present a theory here to you. I will just present an idea of how what graph grammars are and how we can use analysis of graph grammars to analyze different kinds of systems. So this is more or less the idea, so just to have a glimpse of what what this is good for. So as I said, everything in graph grammar, in the algebraic approach to graph grammars is based on category theory. So we have categories of graphs and graph morphisms. And we have different categories of graphs, graph morphism. And then nice thing to use category theory to do this, to build the theory, is that the theory is defined at a very abstract level. So I define what is a rule application for any graph category, and then I can instantiate, okay, now I use directed graph. So I will instantiate this concept of rule and rule application with directed graph. If I want to use hypergraph, I instantiate that concept with the category of hypergraphs. And therefore, analysis of concurrency, of dependency, everything, then will be instantiated for that particular kind of graph that I am using. And this is really nice. I do not have to redo all the theory when I want to switch to a different notion of graph. And the notion of graph is actually a very flexible one. Many things can be seen as graph structures. Many things that maybe, so the notion of a graph is really very broad. So typically when we are defining what the graph is, we want to use types, some kind of notion of type, because when we use types, it is easier for us to specify. I have some kinds of nodes, other kinds of nodes, some kinds of edges, different kinds of, so using different types of edges, different types of nodes makes it easier for us to understand the system. So usually we define a type graph that is actually a structural definition, and then the behavior is defined by an initial graph or start state, that is a graph, and then the rules that describe how the states, how we can transition from one state to the other. So something is very easy. Here is an example of a graph, very easy graph, just two nodes, two edges. So when I say this is a type graph, this means any instance of a state, or any state of my system may be composed of purple nodes and green nodes. And I may have yellow edges and black edges. And if I want to, in any state of my system, yellow edges may only be loops on purple nodes. So this is what this type graph says. So we can then build instances, and so a typed graph is just an instance of the elements that appear on the type graph. So categorically speaking, a typed graph is actually a morphism. A morphism from one graph, any graph to a type graph. But intuitively, it's the same as when you use types in any language. When I use them type numbers, then in any state I may use numbers, and this is the same here. Well, there are different ways to specify rules, as I said, but in any approach, typically we have a left-hand side of a rule that specifies what is needed for that rule to be applied, and we have a right-hand side that defines how the situation will be after the application of the rule. And of course, we have to relate the left and right-hand sides. In the categorical approach, we use morphisms to relate left and right-hand sides. So even in a categorical approach or algebraic approach, we have different ways to define rules and rule application. This SPO, I will say just in the next slide what this means. But we may have a left-hand side that is a graph, a right-hand side that is a graph. Of course, they are typed if we have a type graph. And this relation between left and right-hand side is a morphism that maps everything in the left, that maps some things in the left-hand side to the right-hand side, where everything that is not mapped will be deleted by the rule. Everything that is here in the right-hand side and not in the left-hand side is created by the rule. So it's a very easy notion of behavior specification. So when you apply this rule, that you may have different outcomes. So this SPO that was in that other slide means single push out. I may apply a rule using a single push out. A push out is a construction in category theory. So actually, depending also on the category I'm working, push outs have different meanings. So, but usually when I'm working with categories of graphs and partial morphism or in category of partial morphism, the effect of the push out is exactly the effect that we expect from a rule application, meaning that everything that I have in the left-hand side of the rule, so here is an example of a rule. So this is the left-hand side of the rule. Here is a match. So I find this pattern here somewhere. Here I use this match. When I find this pattern here, what happens is that this edge will be deleted and this edge will be created. And the effect of the push out here is exactly that, to delete this edge here and create a new edge here at this point. So you do not have to know exactly what a push out is, but it has exactly this effect, which is nice because a push out is a general categorical construction, and then a lot of theory about how I can apply rules in parallel or cannot apply, conflicts, dependence, everything can be, I can analyze the system in various ways using, just by using categorical constructions. So from the theoretical point of view, it's very nice that I can specify the rule application as one push out. But I can also use two push outs. This is a so-called double push out approach. And the idea is that a rule is something like this, where you have the left-hand side, a right-hand side, and in the middle are the items that are preserved. So that the items that are here and here. So you have actually a span. And then the idea is that you perform a first push out, and this will delete from the graph everything that has to be deleted by the rule. And then we obtain something that is the state after the deletion step. And then this second push out is used to create items. We can also merge items if you have two nodes and wants to make a join with the nodes, you can also perform this here at this step. So this is a different way of specifying what the rule does. And when we specify like this, your system will have different properties, because if you use two push outs as spans, it's different. So you need some special conditions to be able to perform this kind of constructions. And these conditions will have the effect that the theory of concurrency that you obtain using this kind of rule is different from the one that you have if you only have one morphism from here to here. You can also have different, even different things. You can also use other categorical constructions like the final pullback complement. That is somehow, I will not explain what this is. So, but it is a different categorical construction. And if you use this categorical construction instead of a push out here at this point, you are able to perform copy. With the other approach, you cannot copy items. If you use final pullback complement here, you can say that if I have an item here, I can copy this to this two here. And this will have the effect that in this graph, if there are a lot of edges connected to a node that is copied, if I perform a copy, all the connections will be copied as well. That is usually what you expect when you copy a node. All the relationships of the node will be copied together with the node. So this is to explain you that if I choose different kind of categorical construction, I obtain different kind of effects in my rule application, And of course, the theory that I obtained is a little different because there are, to perform this construction requires a set of conditions that are different from the other of just being a push out here. So, and then the theory is slightly different, but in a way, most of the theory of graph grammars using this algebraic approach is parametrical. Say I have to choose the kind of graph that I want to use. I have to choose the kind of rule, the kind of rule application that I want to use. And then depending on the combination of this, I obtain some part of the theory, other part of the theory. That all the theories are like this. If this and this and this are satisfied, then you can obtain this theory. This theory will be valid in your setting, or that theory will be valid in your setting, and things like that. So this is really very nice because you choose the kind of graph, the kind of transformation that you want to have, and then you obtain the part of the theory or that you get is your choices. But and the semantics of graph grammars is based on rule applications, of course. And then you may have sequential semantics or concurrent semantics based on, so sequential semantics are typically based on performing one rule application at a time. So you perform this and then you obtain this result and then you apply another rule, and then you have the set of all possible sequences that you can get, and this is semantics. Or you may have semantics based on unfolding structures that are the concurrent semantics, and then you actually do not know. You have a set of rules that were applied, and depending on the dependencies that you have here, you can find out which rules may be applied in parallel or not. So we can also, as I said in the beginning, we may have very different kind of graph and different kind of notions of rules. I will say something about this tool, that attributed graph and negative applications conditions that are very useful for practical applications. So we may use notions of, here is an algebraic specification. So you specify data types in some way. And then you may use data types as attributes of nodes and of edges in your system. So here I have a node and I have a natural numbers or stacks as attributes. And then when you transform, when you perform a transformation, you may use even equations here to say, oh, I can only apply this rule if the top of the stack is not this ID and things like that. So you may use equations as to restrict rule application. So in this way, you get a very powerful way of specification, and you can add also negative rule applications that are conditions that should not be present for the rule to be applied. So I may say that this rule have this left-hand side. So can only be applied if I find this pattern in the state. But then this is the negative application conditions that say, okay, I have to find this pattern, but there should not be a green edge here. If there is this green edge here, then the application of the rule is forbidden. So this extension of the theory is very, very useful for practical applications, because in many situations I want to say that I can only add something if this is not already there. So this is a very common situation that happens, and this you can specify using negative application conditions. From the theoretical point of view, this forbidden item, well, is specified like by this by the non-existence of a match from the negative application condition to the current graph. So, but this is not very important for you. Just the idea of negative application condition, I think, is important and is really very useful. So let's stop for a moment and think about what is different from this way of specifying this kind of data-driven languages than other very common specification languages that are process-driven languages, like CCS or CSP, where you specify the systems by using actions that are usually very abstract actions. And typically when you use process-driven modeling, you use operators. You have parallel composition, sequential composition, different choice of operations, and then you specify what the system does by an expression that say, okay, this action may be performed in parallel with this one, and this thing, or maybe there may be a choice or non-deterministic choice or any other kind of choice between this action and that other action. So I explicitly say which actions are to be performed in parallel, or what possible choices my system have. This all is specified explicitly when you use process-driven languages, or process, like any process algebras are this kind of languages. When you use data-driven models like graph grammars or event B is a data-driven also, the system is specified not by an expression on actions, but rather as a set of actions. There are a set of actions that may be performed, and typically these actions are they are not abstract. I do not have an action A and an action B. I have to say explicitly, action A changes the system in this way. Action B changes the system in this other way. Why is that? Because the fact that A and B may or may not be performed in parallel is not specified explicitly in data-driven languages, but it's rather a consequence of these two actions, or these actions do on state, whether these are dependent or independent, or these two actions are in conflict. For example, if two actions want to perform an attribution to the same variable, these actions are in conflict. But I do not declare explicitly in these languages that these actions are in conflict. This will be discovered by analyzing the system and finding out that, well, action A wants to attribute to variable X, and action B also wants to make an attribution to variable X. Therefore, these actions cannot be performed in parallel, or they are in conflict. Therefore, they are in conflict because they are attributions to the same variable. And also parallelism is defined usually by, I cannot have conflict to perform things in parallel, but there may also not be dependencies between the actions to enable them to occur concurrently, so in parallel. So these are different ways to specify systems. I would say that process-driven languages are more abstract, because I abstract away from what the actions actually do, and then describe the system as a relation or about on these actions, or expressions saying, okay, first I do that, and then I do that and that in parallel, and then there is a choice. And so I explicitly say everything that happens. Whereas in data-driven approaches, I do have a set of actions that, in a way, if my system is very big and I have 100 actions, this might be a problem because I do not see actually what is going on. But usually, if you have analysis tools, you can, in a way, recover these parallelism and choices by analyzing this set of rules. So as I will show you now more or less what we can do. So if I have a system, here this a graph, I want to log in, there is a user that wants to log in an ATM machine with a card and a password. This is a type graph saying everything that is all kind of possible nodes and edges that I have in the system. And here I have some rules. And for example, here, the user here has a card, and the system here is in a state insert card, and therefore this is the left-hand side. If the user has a card and the system is in insert card mode, the card may be inserted in a ATM. And this is the negative application condition that says, okay, I can only insert a card if the card is already not in the system. So, okay, so here I have many different rules. I will not explain all of the rules. The idea is just to get an impression of the system. And if I perform some analysis to find out what the conflicts and dependencies I have among this rule, I may reach a graph like this. Okay, this is the result of the analysis. This analysis can be performed automatically. This is a result given by one specific tool. And you see, I can, by analyzing what is each rule, how each rule changes the state, I may find out that ask password rule depends on insert card rule. And that insert password depends on ask password rule. This blue arrows here, they describe dependencies. So this depends on this depends on this. So I can, by analyzing each action that I have in the system, I can build, I can then see something like this, that is a picture of the whole system and the dependencies between the whole system. So this is blue are dependencies and red are conflicts. So I can find out that this rule invalid card is in conflict with validate card, because these are the two possible actions. If you insert the wrong password, you go to this, you perform this rule, and if you insert the right password, you perform this rule. So they are in conflict here. So this is what I meant. We have a set of rules, and then we can infer by analyzing conflicts and dependencies. I can infer things that may happen in parallel or not. For these two cannot happen in parallel, and they are choice points in the system. So, but okay, until now we have a very expressive language, and we can express very complex states using graph grammars and complex behavior. But what can I say about the models? Because it's not enough just to be able to describe the reality. We want to say something. This is one of the reasons why we need to have the formal model, because you want to analyze these models. So there are many different kinds of ways to analyze graph grammars. So I will just speak about one of these three different ways very shortly, such that you have an idea of what can be done. So there are different ways to perform model checking. One that is defined by was to translate graph grammars to different languages of existing model checkers, like Promella, the input language of the spin model checker. There are some works that have done this kind of thing, and then you use that kind of model checker to perform model checking of graph grammar. There are also approaches where we can, this is the Verigraph tool, that is the tool we built in our group, where we can specify your graph grammar, and then we can use model checking tool, usual model checking. You have some property that you want to check, and then you build the state space. Okay, this is example is very small, and then you check the states that satisfy the property, the states that do not satisfy the property. Of course, model checking for graph grammars is a kind of difficult, because as I said, usually one uses graph grammars when you want to have a very rich description of your state. Your state have many relationships, and you want to use data types. And if you have a very rich description of states, model checking starts becoming not really feasible because of states, problems with state explosion. If you have really many different states, and very, very quickly you cannot say anything else with model checking. Therefore, for graph grammars, other kind of techniques are more useful. For example, theorem proving. So well, you all know that theorem proving is a very powerful technique. It's very general. You can use it to perform prove properties of infinite state systems. And it is complementary to model checking and to static analysis. These are all different ways of proving properties. Some properties are much easier proven by using theorem proving, and others are using model checking or static analysis. Theorem proving involves typically more some knowledge of proving. Model checking, no. Model checking, you just have to be able, at least, okay, you have to be able to state the property, which is not always very easy. But then the model checker performs automatically. With theorem proving, this is not the case. We have used the event B to prove properties of graph grammars, the event B infrastructure, because the event B is very close as a modeling language to graph grammars. Because in event B, you have states that you are specified by variables, not by graphs. And the states changes the attributes of that variables. And what we did was then to encode all the graphs and graph morphism in the notion of states of event B, and the notion of rule application in the notion of the events in event B. So this was done in a way, easy way, because they are very close. And then we were able to use event B to prove properties of graph grammars. So the idea was first, as I said, I have the graphs and the rules, and there is a part of the graph that doesn't have any attributes. And then all these were translated. And then all the parts with attributes that are data types and everything, equations and rules, this was modeled as context extension and machine refinement, which is very good, because this means that all the properties that I can prove just based on the graphical part of my specification will remain valid if I add the attributes. So if I have a token ring specification, and the token is an edge, and I can prove that there is at most one token at each state in any moment in my system, and I can prove this just using this part of the specification. It is independent. If I add data types and then more properties on data types, I do not have to prove again that property, because this is just an extension with respect to the original theory. And typically, properties that are just relying on structure are easier to prove than properties that have to deal with also with data types. So that's why this is really so important to do. So I'll just show you more or less how this looks like. If I have a graph here, I can just build a very easy, this is, no way, maybe it's not easy, but it is straightforward. A graph is a set of vertices, a set of edges, and functions that connect each edge to a source and to a target vertex. And this I can specify in a natural way in event B. So there are sets of vertices and sets of edges, functions that connect edges and vertices. And here we have for this specific graph, this is the description, the event B description. Of course, we have a general definition for this translation. This is just an example. For data types, it's very easy, because if we have an algebraic specification of that data type, you can translate in a straightforward way to an event B context with the operations and constant and so on. And for the rules will be translated to events in event B. In a way, I have to specify the left-hand side of the rule as a graph. And then here I say, whenever I find a match, the event is the application of the rule. So whenever I find a match of vertices and match of edges, in an actual graph G, then I can perform this. I can change this state, that is a graph, to this other state, which is another graph. The effect of the application of the rule is given here. This rule only adds two edges. This is an edge and this is an edge. So I take the original set of edges and add these two edges. Of course, then I have to change the source and target functions and typing. But here, what we have here as conditions for the rules to be applied, these are actually the equations that assure that this is actually a graph morphism. So we are dealing with categories. So I do not want any M and V functions, but this may be a morphism, and there are specific conditions that I require for this to be a morphism, and these are specified here. So this is a concrete example that is also, we defined this as a general procedure, so this can be automatically generated, this translation. So, and for the attributes, the same. So I have to translate the attributes in a canonical way to event B event. So I have to translate the attributes, also the equations. The negative application condition, if I have a negative application condition, this will be translated by a guard of an event, because this is something that cannot happen. I cannot find an edge in this graph that is connected to this node, an edge of this kind that's connected to this node. So it's an additional guard to the event. So NACs are very easily translated to event B conditions. And then I may prove many properties. Here are examples of some properties that we have proven in a token ring example. There are properties that are properties of the graphical structure, or there is only one token at each state. There is at most one active station holding the token, and there are different properties involving attributes. I don't know, any node cannot have two different node IDs and things like that. So we performed this translation of many examples to the Rodin. And here is some, just to have a glimpse of what happens when, if you know something about theorem prover, we get a lot of proof obligations when we perform this translation. Many of them are automatically discharged. Some of them are easy. By easy, I mean I just have to enter there and click implication or do some instantiation, then are easily performed. And for some of the proof obligations, one has to think and about the problem and aid the prover to conclude the proof. Just that here I just make all these proof obligations are related to the structure, to the translation. And actually, okay, I may, these proof obligations will always be dischargeable. They are true. So if I do not want to prove this one, I don't have to, because they are just consequence of the translation, and we have proven that the translation is correct. So it only generates correctly correct typed things. So, but anyway, some proof obligations are generated, and we may prove them. So, but these are not related to the application itself. These proofs obligations are related to the applications, to the properties that we state. And you see here that a lot of properties are related to the attributes. So the properties that one has to prove attribute contents. So static analysis, so just to tell you a bit about static analysis. Static analysis is totally automatic. It's not, you do not have to aid the system. And it's based on, basically in graph grammars, on what we call critical pairs and on concurrent rules. Critical pairs, I already said more or less what conflict and dependencies are. So this is a critical pair. When I have a rule that says that this edge, this blue edge, will be deleted, and this other rule also performs an action. I know this is the dependence. This is a critical pair because this deletes this item and this preserves this item. So I cannot. It is not possible to do these things in parallel. I may do this and then that in this order, but I can the other way around is not possible, because once I deleted this edge, this rule is not applicable anymore. So this is a situation where we call a weak conflict, because it is not symmetric. There are conflicts that are symmetric. This one is not. And this is a dependency. This rule generates an item that is needed by this, and then this generates a dependency. This dependency, when we speak about critical pairs, we are talking about potential conflicts and potential dependencies, because this is at rule level. It may be that in a concrete situation, there are many Pac-Mans that may in a graph, and then I may apply a move operation and a knit operations, and they are totally independent. But there is a potential that I can try to apply these two rules exactly to the same portion of the graph, and this will generate a dependency. So dependencies and conflicts are, when we perform analysis at the analysis level, are all potential. Okay, so there are tools to automatically find the critical pairs, dependency critical pairs, or conflict critical pairs, and then these tools say exactly which parts of the graph these dependencies or conflicts occur. And typically they show the results as matrices. So this is one tool, the result, this is another tool that is. And we also may build concurrent rules. Concurrent rules are rules that I build with a sequence of rules, and then I build one rule that has the effect of all those rules applied in sequence. This is also very useful for specification, and I will just show very quickly what we can do with this kind of analysis. For example, we use this kind of static analysis to analyze use case, analyze and improve use cases. Use cases, everybody knows what they are. And our idea was to translate use cases to graph grammars, analyze the use cases using static analysis, and then correct the use cases, because usually use cases are written in natural languages, and they are many times ambiguous, or they have problems, they are inconsistent. So our idea was to do something like this. And then we do this via serious steps. I will not go through. I just want to show the result. That our idea was we translate the system to, I will show the other slides here. Oops. Translate the system, the use case, to a set of rules. And then we analyze these rules as a graph grammar, use use case effects, so concurrent rules and critical pairs. And then we analyze the results. And then based on these results, we have different kind of problems that we can find out. So this, when we have something like this, if we build a concurrent rules, the concurrent rules is like this, then actually this is the problem that you have. Here we classify the levels of the problems that we found out, and said which kind of action the user could do to prevent this problem of occurring. So there are many different kinds. These are all kind of problems that we may find out analyzing concurrent rules. And we also have kind of problems that we that we find out, you analyzing this kind of matrices of conflicts and of dependencies. Okay, this is already said. So we have a lot of we call open issues. Okay, if a rule is not in conflict with itself, this is something that we find out, then this means actually that this rule could be applied in an arbitrary number of times. And this may be the desired behavior, but usually is not. So we just say, okay, the user should look at the specification to check whether this behavior is really the expected one. So in this case, the severity level is yellow because this might be the case that you really wanted that. But there are some actions that you actually do not want, and then you have these different severity levels. So dependence you can do in an analogous way, and we perform this kind of analysis on many different use cases, and we found out that in the real use cases used in the industry, and we found out that most of them, or many of them, were wrong, have the missing parts or ambiguous parts, and so we have to add things. So this really would help to do this, perform this kind of analysis. And the analysis is not really difficult. This analysis is easy. Of course, you have to make this translation step to graph grammar, but once you have this, then the analysis is easy to do. We could also use the same kind of analysis to perform evolution. So evolution of meaning that I want to change a system. So I want to perform a change, and therefore I probably will have to change all the use cases of my system because I want to perform this kind of change. So specification of evolution is difficult, and what is more difficult is to understand what will be the effects of the evolution on the overall system. It may be that I want to perform some kind of evolution and I think, okay, this is not a problem, it's just changing this. But once you check the whole system, you might find out that this small change will have impacts in many different parts of the system. So this is the idea of specifying evolution, and we specify evolution as a second order rule. So a rule that changes other rules of the system. And since I told you, graph grammars are usually done at a categorical level, we just change the category. So we have a category of where the elements are graph grammars, and then we consider which would be the possible conflicts and dependence among different graph grammars. So we apply exactly the same theory to a different to the different kind of graph that are graph grammars, and then we obtain the results of the tools perform exactly the same, and then we obtain different results. So for this higher level situation, this I wanted to just to say that one could do this, and this is really very nice because you can use the same theory, the same tool, and then obtain results at a different level of abstraction. So these are evolution, also, I mean, rules that change rules of the system. So we did the same thing, and then we can perform this at this level. And here, okay, we have different kinds of conflicts because we may have conflicts among evolution rules because we may have different rules to specify my evolution, but I could also analyze how the evolution will change the behavior of the regional system. And this is, I can find this by checking the dependencies and conflicts between second and first order rules. If there are dependencies and conflicts here, this means that my evolution affects the behavior of that rule. And then I have to check whether this is actually an intended behavior change or if it is a mistake. I wanted to change something and then as a side effect, I changed the behavior of other rules. So this is very nice that I can detect this kind of things. And I will not go into details because I want to show you a last example that is really nice. We use the same approach to validate medical procedure documents. And medical procedure documents are actually descriptions of how a procedure should be performed. Medical procedure and this procedure is performed by doctors and by nurses, not by computers. But when clinical trials are made, clinical trials are usually, many of them are huge trials involving many doctors and many nurses in different states, different countries, and so on. There must be a patronization that every nurse, every doctor that performs the procedures should proceed exactly in the same way to prevent invalidation of the experiment. And this is really very important in medicine. Actually, we did not know that. So here, this work was done together with doctors from the Fiocruz. Here is some institution in Brazil where they do a lot of things in medicine and biology. And this is nice because something that we show that formal methods, you can apply formal methods in many different contexts that are not just computational systems. And what we did here was exactly the same. We took the guidelines, so the instruction, the medical procedure, translated to use cases, and then we used graphical symbols that has some meaning for them. So we had the doctor, the syringe, the lidocaine and things like that we wanted to perform, build the type graphs, and then some rules. And the nice thing was that we could show the rules to the doctors and nurses and asking them whether our specification was really okay. And they could understand the specification, say, okay, this is exactly what we do. We do this, if we are in this situation, then we do this, and at the end we are in that situation. So this was very important because we had to validate our model with them to check whether this is really the model that they thought they were building. And then we build concurrent rule, build conflicts and dependencies graphs, and we found a lot of open issues, and the open issues discussed it with them, and they were really real problems in the medical procedure that they were defining. And with this, we could revise the use cases and so on. And we found out during this is that in medicine, they do have standards of description of medical procedures, and gold standards for description of medical procedures require formal verification. They do need, so they do need this kind of thing. So this is really an application field for our techniques that we should consider. So in like this, I think that maybe many other different kind of application areas that may be there, and we do not even know. And maybe, like in this medical procedure, just simple notions of it. We do not need very involved theory to be able to apply and get real results that really help people doing things. So my message here final message is, try to use your modeling languages and your formal verification techniques in different contexts, not only in computer science, because I think there we will find out that there are lots of things more that we can do with what we have. So I think I'm already out of time. Thank you very much. Your mic is not working, I think.
Yeah, I'm making a long speech here and my mic is not working. Yeah, so thank you very much. It was a very interesting talk. And let's see if people have any questions. Well, I have a few questions. I think it's very, very interesting work that you do. And I see a lot of similarity with the traditional model checking work that I and other people do. I thought it was very interesting. I particularly liked your example, your medical example. I've also been working with medical software, but not on the formal methods area, but so perhaps we should talk. And a question for you is, what tool did you use to reach those results? Did you use theorem proving, or how was it done?
In the medical case, no. We use, because we just performed static analysis here, conflict and dependence detection. So we just used for this one, was that this AGG tool, that is a tool from the Technical University of Berlin. And we also built a tool, our own tool, that is called Verigraph, that is built in Haskell, is much more efficient than the other ones. But then this was nice, because just using static analysis and simple things, we reached results that were very, very useful for them. So, and once they could show that they formally verified their procedures, they reach a different standard. I didn't know that they have this kind of levels of standard of specification medical procedures. So for serious clinical trials, they do need this kind of things. And it's just like a use case. So it's really, for us, it's a very nice field to work on. And we are doing research that is really applied in saving lives. This is nice.
That's true. That's true. Yes, very interesting. So the simpler tool, between quotes, of course, did the work. Yeah. I was at a conference once, and it was a biological conference, and people were claiming that the area needs strong, large graph databases and tools. Mm-hmm. So there's a lot of application of graphs and graph grammars in other biological areas. These biological systems, they have really large set of entities, and the relationship between them is not simple at all. So this kind of tools would be of big help. So yes, thank you very much. This was very interesting. Does anyone else want to ask a question?
I may have a very, may I, Sergio?
Gustavo, yes, of course. Please,
it's a very short one. So Leila, you have, first of all, thank you for the very interesting talk. You have mentioned that you have translated some of these rules into event B, right?
Yes.
So my question is, what is the rationale for not using classical B? Is this related to some concurrency that you are seeking for?
Event B is much closer to graph grammars, because you already have this notion of event. So, okay, the state is, you have the notion of state, that is, we translated then the graph or the state graph to the state variables of the event B. And then you have the notion of event that is exactly, you can use to describe rule application. And this made it much, much easier to make the translation and prove that the translation is correct. So this is something that I usually insist on. I do not like to translate things and without proving the correctness of the semantics of the translation, because otherwise, what's the point of translating if you cannot prove that you preserve the semantics in this translation? And the semantics of event B is much closer to the semantics of graph transformation, because you have a transition system there. So it's really much easier to do. And we found, of course, there is this, and we also have the other things that are not technical, but we are working with event B, because when we went to UK, then we had a connection with Newcastle. So we work with them and they work with event B. So we started working with event B together with them. And so it was really somehow, use it event B. So easier to.
Okay, thank you.
Okay, so let's thank the presenter, elderly for all the people. And that concludes our session now. And we should be back, well, in 15 minutes because we started late. But
okay, thank you very much.
Here. Bye-bye.